Here's the question. Now consider a binomial probability mass function and show that mean is n times p. So first, I want to find the expectation. The expectation from the basic definition is all the possible outcomes times their weightings. And that's for all the possible outcomes here. And for the binomial, we know the k is from 0 to n. And all possible outcomes is still here, k. And the PMF is n choose k. Probability k times 1 minus p, n minus k. Here we extend the n choose k. So it's still summation here, k equals 0 to n. So it's n factorial divided by k factorial times m minus k factorial times k. And the probability p to the k times 1 minus p to n minus k. Seems I can cancel that. This one and this to have a k minus 1 factorial. So I will have k equals 1 to n. Then here is n factorial k minus 1 factorial m minus k factorial p to the k 1 minus p n to the k n minus k. Here we can do some arrangement. Since I have n minus k, the strategy right now is to have the m minus 1 choose k. Want to create m minus 1 choose k. So first step, I take n, just n out, still k equals 1 to n. Now then I have m minus 1 factorial, k minus 1 factorial, and m minus k factorial, p to the k and 1 minus p m minus k. Next, I want to have the k prime equals k minus 1. What happened? I still have n and summation because k prime is k minus 1. So I have k prime equals 0 to m minus 1. You see here, we change to k prime equals 0 to m minus 1. Also, I still have m minus 1 factorial. Then here, k minus 1 factorial becomes k prime factorial. Also, m minus k factorial becomes m minus 1 minus k prime factorial. And also probably a p to the k prime plus 1 and 1 minus p n minus k prime minus 1. So now I have this expression, but here I have k prime plus 1, p to the k prime plus 1. I want to take just one p out in front of the summation. So here becomes n times p, and here's k prime equals 0 to n minus 1 factorial k prime factorial n minus 1 minus k prime factorial, and p to the k prime times 1 minus p n minus 1 minus k prime. What is this? If you can look at seriously, this is the PMF. It's also a binomial PMF of K. And K is from 0 to n minus 1. So this is a valid PMF. So from the property of the PMF, if I summation all the PMF, this summation becomes to 1. So finally, the answer is n times p. If you don't know why this is still the PMF, we can think in this way. If I have n minus 1, it's like a big N factorial. N, and here's n. So it's the same as this expression. Right? Oh, and also because here I should have an n minus 1. And I think, here's n minus 1. So I have here n minus 1 is n. So it's exactly the same here. So the expectation is n times p. Next, consider the geometric PMF and show that the expectation is 1 minus p divided by p. Again, when we talk about the expectation, when we want to calculate it, follow the basic definition is consider all the possible outcomes times their weightings. The weighting is just PMF. From geometric, K is from 0 to infinity. So it's all the possible outcomes. K is from 0 to infinity. Then once you have this formula, then you plug in. Don't be in a hurry that just plug in as quick as possible. You just write it down this formula and then you plug in. That will be easier for you and won't be confused. So K is from 0 to infinity. Since P is nothing related to the summation of K, so I take P outside the summation. So here's K times 1 minus P, K. Now I just substitute the changing variables that Q equals 1 minus P. So what happened, as you can see, I still have a p outside. Still have a p outside. Don't care about this. And then k is still from 0 to infinity. And then k, then here is q to the k. Wow. And I think the k should be from 1 to infinity. So seems k is from 1. Because if it's 0, it doesn't, it's still the same. Well, 0, when we plug in 0 here, and it's still 0. So k equals 1. Now I can have like p times q. I take one q outside. We don't need p. You just leave p here, and then we will let the q later to be 1 minus p. So if I have one q outside, here is k times q to the k minus 1, k from 1 to infinity. Why we want to do this? Because if you expand the summation, is 1 plus 2q plus 3q squared plus to the infinity. This we did it in homework 1, and we know this summation is 1 minus q squared in the denominator. 1 over 1 minus q squared. And when we we just plug in, substitute q equals 1 minus p, again, back. So it's p times 1 minus p. Here is 1 minus p squared. Finally, we will get 1 minus p divided by p. For the discrete random variable, we must know the binomial PMF, geometric PMF, and the next is Poisson PMF. And we want to show that the variance of Poisson random variable is lambda. And actually from homework 1, we know the expectation of random Poisson is lambda. Also, the expectation of x squared is still lambda squared plus lambda. So the variance of x is lambda squared plus lambda minus lambda squared is lambda. Please do check your homework 1 and see how you get the expectation of Poisson random variable is lambda. And for D, it's a uniform PMF. Show the variance, and there's a hint here. So to show the variance, first we need to find the expectation, because we will use this formula. The expectation is all the possible outcomes times their weightings. Here k is from 1 to L. So we just plug in, because pk, the mass function is 1 over L times k. K is 1, 2, 3 to L. Then this is L plus 1 divided by 2. Now for the same thing, to compute the expectation of x squared, consider all the possible outcomes squared times the weighting, and k is from 1 to L, because all possible outcomes. Then here is like 1 squared plus 2 squared plus L squared. Then you will get L over L squared over 3 plus L over 2 plus 1 over 6. And then finally the variance is just the expectation x squared minus the mean square, which is here.